Hello everyone, let us discuss few more examples of set theory to give you a little more clarity on things. Let's suppose this is first example which is actually asking you that which write the following sets in roster form. This is also called as a tabular form. And in writing the tabular form, the first question says x such that x is an integer between -3 and 7. So I would recommend the students immediately put up a number line, see that where the 0 is lying, -1, -2, -3 is here, and so on. And here it is 1 2 3 4 5 6 7, and this clearly says I have to write the numbers between -3 and 7, including, this is a less than equal to sign, that means including -3. 7 is excluded because this is a less than sign, not equal to 7, only the numbers less than 7. So you can you can simply write a as -3. You can see in the number line -3, -2, -1, 0, 1, 2, 3, 4, 5, 6. 7 is not included. So -3, -2, -1, 0, 1, 2, 3, 4, 5, and 6. So this is the roster form or tabular form of this particular set. Let us see second set. B is equal to x such that x is a natural number less than 6. Again, very simple. What are the natural numbers less than 6? 1, 2, 3, 4, and 5. So easily all the elements of the particular set are listed and the set is represented in a roster form. Let's see the next example. X such that x is a two-digit natural number such that the sum of its digits are 8. So it's a two-digit natural number. So and the sum is supposed to be 8. So how you are going to write this particular set? So if I start with first natural number 1, then 1 plus 7 is 8, then 2 plus 6 is 8, then 3 plus 5 is 8. I'm increasing the natural number, the first natural number. After 1 I'm moving to 2, 2 to 3, 3 to 4, then 4 is 8, then 5 and 3, that means 53 is 8. If you total 5 and 3, then 6 and 2 is 8, 62 is 8, 7 and 1, 71 is 8, and 80, 80, this is also 8. Moment you reach from 8 to 9, we are going to enter into the 90s and the sum is going to be more than 8. So this cannot be included. Let's see D. X such that x is a prime number which is divisor of 60. Simply you just need to factorize 60, and that is the best way to do it. Let's say 2 30 times, and 2 15 times, and 3, and it is 5 times. So fundamentally for 60 you have the calculations such as 2 times 2 times 3 times 5. So x is a prime number which is divisible of 60. So there are three numbers which I am getting, 2, 3, and 5. Remember, do not write 2, 2, 3, 5 in roster form, because sets definition says there is supposed to be distinctness. That means no element should be repeated. However, 2 is coming twice, but I am going to write it only once because it should not be repeated. So it will be 2, 3, and 5. Let's go to next particular example. E is equal to the set of all letters in the word trigonometry. So I'll start with first one. T, it's a letter, member of the set. R, absolutely fine. I, absolutely fine. G, fine. O, fine. N, fine. O, already covered. M, not covered, write it. E, not covered, you can write it. T, already covered, no need to write it. R, already covered, no need to write it. And Y. I'm managing the property of distinctness. That means every element should be unique. Nothing should be repeated in a set. Let's say F, the set of all letters in the word better. So I'll also use the same method. I'll start with B, E, T should be written. Again T, already covered. E, already covered. And R. All the elements are supposed to be unique and separated by a comma. Let's see. We know the definition of null set. Null set simply means the set which doesn't include any element at all. It is also represented by phi or two curly brackets which having no element in between. So any set which doesn't have any member in it, becomes a null set. You can refer to the previous video if you want to see it. So first is set of all odd numbers divisible by 2. We already know there is no odd number which is divisible by 2. So it is a null set. You can represent it by like this, or you can represent it by a letter called phi. Set of even prime numbers. I know there is a number called 2 which can be a member of this set. So it is not a null set, not null, not an empty set. There is a member in it. X such that x is a natural number which is less than 5 or greater than 7. So if I look into the number line, it is 0, 1, 2, 3, 4, 5, 6, 7. So it is saying x is a natural number less than 5. So less than 5, 4, 3, 2, 1, and greater than 7. That means it is supposed to be 8, 9 or something, whatever it is. So there is no number which is less than 5 or greater than 7. There is nothing. So it is again a null set, can be represented by a letter called phi. Y such that y is a point common or to any parallel lines. Two parallel lines. So these are two parallel lines. Can you think that there is any common point between them? No. The line should intersect to have a common point. So this is again a null set. There is no possibility that two parallel lines have a common point. Again, which of the set is finite or infinite? I clearly know that if I can count the number of members, it is finite, otherwise infinite. And here it is clearly visible. Set of months of a year. I know that there are 12 months in that, and that is called January, February, March, April. And it is exactly going up to December. So there are two cardinal number of this set. If you want to know the cardinal number, you can refer to the previous video. There are 12 elements in it. I can count them. So it is finite. 1, 2, 3, and so on. I'm not sure where it is ending, going up to infinity. It is simply an infinite set of natural numbers. 1, 2, 3, 99 up to 100. I know there is a lower limit, there is an upper limit, and these are the natural numbers. So I can easily see that cardinal number in this is going to be 100. So it's a finite set. I can count. The set of positive integers greater than 100, no, it's not finite, it is infinite. So if I start writing on the number line 4 and so on, it goes up to 100, and over 100 it can go up to any limit infinity. So it is again infinite. Set of prime numbers less than 99, I can simply count them, right? So less than 99, there could be primes like 1, 2, 3, and so on, whatever primes are going to come. So all these numbers are the prime numbers, right? I'm not sure one is going to be counted or not, but I'm saying overall that less than 99, that means below 99, all the primes can be counted. So it is again a finite set. Let's see the next example. State whether each of the following set is finite or infinite. Set of lines which are parallel to x-axis. There can be as many lines as I can draw parallel to x-axis. It is infinite. The set of letters in English alphabet, I know there are 26 letters, so it is finite. The set of numbers which are multiples of 5, infinite. Again, it is 5, 10, and so on. You can continue doing it. So it is infinite. The set of animals living on earth, definitely we can count them. Finite. Set of circles passing through a line. So if this is 0, 0, so how many circles can pass? N number of circles can keep on passing. Means there are infinite circles. So it is again an infinite set. Let's see whether the two sets are equal or not. And the definition of equal set is very, very simple. If x belongs to A and x belongs to B, that makes it A is equal to B for all x in A and B. So simply the member should be of in A also and B also. Order doesn't matter. So A is in A, it's also in B. B is in A, it's also in B. C is in A, C is in B, D is in A, D is in B. I can simply write A is equal to B. Correct. 4, it is here. 8, it is here. 12, not here. That means 12 is in A, but 12 is not in B. Therefore, A is not equal to B. A is 2, 4, 6, 8, 10. X such that X is a positive even integer less than 10. So what is an even integer? So if I write B in the roster form, it makes the life easy. Even integer less than 10, less than or equal to 10. So it is going to be 2, 4, 6, 8, 10 simply. So if you see 2, 2, 4, 4, 6, 6, 8 is here, 8 is here, 10 is here, 10 is here, and you can simply say A is equal to B. Correct. Checked. X says that X is a multiple of 10 and B is 10, 15, 20, 25, 30. So what are the multiples of 10? If you start writing A, it is going to be 10, 10, 20, then 30, then 40, and I don't have to calculate much. I can simply see, this is B, and I can simply see 15 is here in B, but it is nowhere in A. And I can simply say 15 belongs to B, but 15 does not belong to A. I don't have to see more than that. Simply I can write therefore A is not equal to B. Thank you. Let's see more problems in the next lecture.